So far in the last class, we discussed the introduction to physical spectra, that is, introduction to physical spectra, that is, all points, electromagnetic radiation, classification of electromagnetic radiation, and related problems. Relative problems, Lambert-Beer law, and related problem was the last of that class. Now we will start with the some more problem of Lambert-Beer law. Now, an organic compound an organic compound having epsilon is equal to 7,000 molar inverse per centimeter inverse give a absorbance of 60% at concentration of 0.01 molar. Determine the molar mass of organic compound. Determine the molar mass of organic compound if optical path length is 10 centimeter. Then what will be molar mass? Now, according to Lambert-Beer law, A is equal to epsilon CL. C is equal to A upon epsilon L. Sorry. That is. Now, sorry. 0.01 milligram at amount of 0.01 milligram, 60%, 0.6, 7,000 molar inverse, centimeter inverse into 10. That is, C is equal to 0.6 by 7 into 10 power minus 4 molar. But concentration is equal to number of moles per unit volume. Now, C is equal to amount of substance divided by molar mass. That is 0.6 upon 7 into 10 power minus 4. That is, molar mass of organic compound is equal to weight 1 into 10 power minus 3 divided by 0.6 by 7 into 10 power minus 4. Or ये आ जाएगा, that is molar mass is equal to 70 divided by 0.6. That is molar mass will be anyone, क्या हो जाएगा? What will be molar mass? 116.66. 116.6 gram per mole. So molar mass of organic compound, that is identification of a known organic compound on the basis of molar mass, can also done by Lambert-Weir law. Two very interesting problems. One is from, I think it was from TIFR, Tata Institute of Fundamental Research का entrance. That is, whenever electromagnetic radiation is passed through the surface of ocean, at a certain depth, its intensity become 10% of initial determine the depth. Epsilon for water is 2 into 10 power minus 6 meter inverse per centimeter. What will be depth? That is 90 meter, 90 centimeter, 180 meter, 180 centimeter. These are the four options. Now, A is equal to epsilon CL. Now we have to determine the L. A is equal to log of I naught by I. Epsilon CL, where I naught is incident. I naught is intensity of incident radiation and I is transmitted radiation. Now, log of L is equal to log of I naught upon I divided by epsilon into C. Now log of I naught upon I naught by 10, because 10% ही रह गया. ठीक, that means reflected radiation has a intensity of 0.01 I naught. Now divided by 2 into 10 power minus 6 molar inverse centimeter inverse. What is the concentration of water? What is the concentration of water? Anyone?
55.5.
55.5. 55.5 is concentration of water, molar, or that is L is equal to log 10 divided by into 10 power 6 divided by 2 into 55.1, 55.5 centimeter, और that is equal to क्या आ जाएगा आंसर? कौन सा ऑप्शन होगा? Which option will be correct?
90 meter.
90 meter. That is 9,000 9,000.9 centimeter, or that is equal to 90.009 meter. So we have only one option, that is A option is here correct option. So this type of problem is also asked here. Trick was that is concentration of water. And here we have to utilize the concept that A is equal to log I naught by I. Now, another last problem. Afterward, we will move to new section. That is, a radiation is successively passed through the blue filter, blue, red, and yellow filter. A radiation is successively passed through the blue, red, and yellow filter. If transmittance of blue filter is 35%, 60% red filter, and 30% yellow filter, what will be net absorbance? Net absorbance. Net absorbance क्या होगा? What will be net absorbance? Transmittance is equal to I by I naught. And it is I1, I2, I3, or it is equal to I1 by I naught into I2 by I1 into I3 by I2. Transmittance is a multiplicative property. Transmittance is a multiplicative property. ये देखिए, I1 cancel, I2 cancel. Finally we get I3 upon I0. Now, transmittance, net transmittance is equal to T1 into T2 into T3, or that is equal to 0.35, 0.60 into 0.30, or that is equal to 0.063. 0.063 net transmittance. But it is not your answer. It is not your answer. You have to calculate the absorbance. So, what is the relationship between absorbance and transmittance? A is equal to log I naught by I, or log of 1 upon I naught, or that is equal to log of 1 by T. This is the relationship between absorbance and transmittance. Now, absorbance is equal to log of 1 upon 0.063. That is equal to क्या आ जाएगा? क्या आ रहा है? What is the answer? 1.200. 1.200. That is the absorbance. A student may calculate absorbance A1 by the 35% transmittance, absorbance A2 by the 60% transmittance, homework, and absorbance 3, that is through the 30% transmittance, and compare the individual value by this. You will get less absorbance as compared to this. And that's why we use successive filter in the spectrometer. We use monochromator. We use monochromator and grating. Monochromator and gratings. Very fine filter. Very fine filter. Or a arrangement of successive arrangement of prism. Prism you must know. Prism use किया भी होगा. So we use the prism for increase the absorbance, because absorbance increases as the number of filter increases. So that is problem related to the use of filter in a spectroscopy. Now, you can also solve problem on Lambert-Beer law by through our assignment, and in any doubt you can ask from me. Now, next is that is, Band broadening. Band broadening in a spectrometer. Sharp band spectra. Sharp band. Broadband. 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 Spectra. Sharp band, broadband. It is called as sharp band spectra. It is called as broadband spectra. What is the reason for band broadening in a spectra? Generally, molecular spectra are broadband spectra. Atomic spectra are sharp band spectra. Broadband spectra. One of the major reason for band broadening is Heisenberg uncertainty principle. Uncertainty principle. Heisenberg uncertainty principle. That is the. What is Heisenberg uncertainty principle? You must know about this. Heisenberg uncertainty principle. Heisenberg uncertainty principle is delta x into delta px is greater than equal to h upon 4 pi. Energy of a system is equal to half mv square is equal to p square by 2m, where p is momentum. Taking the first derivative, delta E, p square, 2p, delta p by 2m. That is p delta p upon m. But what is momentum? Momentum is p is equal to m into v delta p divided by m, or that is equal to v delta p, where v is velocity. Now, velocity is equal to distance traveled upon time taken into delta p, or we have delta E into delta t is equal to delta x into delta p. Replacing this, if delta E into delta t is equal to delta x into delta p, we can remove delta x delta px by delta E delta t, and we get delta E into delta t greater than equal to h upon 4 pi. This is the basic of, this is the HUP applied to spectroscopy, applied to spectra. Delta E is uncertainty in energy. Delta E, uncertainty in energy. Delta T, uncertainty in time. That is called as relaxation time. Relaxation time or lifetime. Lifetime. How will we use this? What is energy of electromagnetic radiation? Energy of electromagnetic radiation is equal to Hc nu bar or delta E is equal to Hc delta nu bar put in the value of delta E. We have Hc delta nu into delta T must be greater than equal to H upon 4 pi or H cancel delta U delta nu bar into delta T is greater than equal to 1 upon 4 pi C. This is the Heisenberg uncertainty principle for band broadening. It is Heisenberg uncertainty principle for band broadening. That is 2.65 delta nu bar into delta T is greater than equal to 2.65 into 10 power minus 12 centimeter inverse. Second, that is the delta nu bar is called as bandwidth. Bandwidth. Delta T is equal to time. Relaxation time. Relaxation time or lifetime. Very important formula from our physical spectra point of view. 2.65 picometer per centimeter. Second, like very simple case. Determine the bandwidth of a NMR spectra. Bandwidth of a NMR spectra having lifetime of 2 into 10 power minus 6 second. That is bandwidth delta nu bar is equal to 2.65 into 10 power minus 12 centimeter inverse second divided by 2 into 10 power minus 6 second, that is equal to 1.325 into 10 power minus 6 centimeter inverse. NMR spectra. Band broadness is this. NMR. NMR. Now calculate band width of a electronic spectra. Electronic spectra. Having lifetime of 10 power minus 12 second. That is delta nu bar 2.65 into 10 power minus 12 divided by 10 power minus 12, 2.65 centimeter inverse. Where band is more broad? Where band is more broad? It is two-way communication. So, in my class, use the mic to give the answer also, because it is physical chemistry. The class must be live from the both way. In which case band is more broad? In which case band width is higher? Band width is higher in this case. Here almost it is a sharp band. Almost sharp band. Of NMR spectra you are using. At least you have seen in the book. NMR spectra. How it look like this. UV spectra. You must have seen in the book. It is like this. Inherently. And it is due to this. It is due to this. That is, band width is inversely proportional to lifetime. If relaxation time is high, band width will be small. If relaxation time will be low, band width will be high. Relaxation time, delta T, electronic, less than vibration, less than rotation, less than NMR. Therefore, band width higher in electronic, vibration, rotation. Inherently, we cannot do anything. Electronic spectra will be broadband spectra. NMR will be NMR, ESR will be sharp band spectra. Inherently. Now, broadness can be decreased in electronic spectra by other method. But overall, electronic spectra remain a broadband spectra. State of matter. The first point is that is electronic spectra, vibrational spectra, rotational, NMR, ESR, bandwidth decreases in this order. State of matter, gas, liquid, solid. In the gas phase, all molecules are separated widely. In the gas phase. So relaxation time is high. Bandwidth will be low. In the solid state, there is compact packing of molecules. Solid, compact packing of molecule. So that one molecule can transfer its energy to other molecule. And undergo relaxation. In a process called as lattice relaxation. इसी को कहते हैं lattice relaxation. Therefore, relaxation time is very low and spectra is broadband spectra. That's why we generally try to take a spectra in the gaseous state. If gaseous state cannot be achieved, we prefer to take a spectra in solvent phase, so that moderate effect will be observed. But solid state spectra is only rare case. If we have no other alternative, then we take a spectra in the solid phase, and band broadening is managed by other factors. ये देखिए गैस फेज स्पेक्ट्रा, लिक्विड फेज स्पेक्ट्रा, solid phase spectra. That is the difference in the bandwidth. Now, problem related to bandwidth. Two NMR spectra having lifetime of 10 power minus 3 second, 10 power minus 6 second, determine the ratio of bandwidth. 1:1000. B 1:10. C 1000:1. D 10:1. That is delta, delta nu is inversely proportional to delta t, or delta 1 upon delta 2 is equal to delta T2 upon delta T1, or that is 10 power minus 6, 10 power minus 3, or that is equal to 10 power minus 3. That is delta 1 is to delta 2 in proportion of 1 is to 1 upon 1000, or that is delta 1 is to delta 2 is in proportion of 1000 is to 1. Which option? Which option? C. It is simplest of the problem. Simplest. Only thing we have to keep in the mind that we have to determine the delta ratio of delta nu bar upon delta nu 2 bar, not opposite, and it is inverse relation. It is inverse relation. Now, one more problem that is very difficult to understand, that it is problem from the physical spectra, and you will blame for coordination compound, sir. That coordination compound, sir, does not teach this topic, but that blame will be wrong because it is problem from my topic. That in the complex of titanium, H2O 6 plus 3, two bands are observed at 20,500 and 20,300 centimeter inverse. Calculate the minimum time interval. Calculate the minimum time interval to observe these two peaks independently. Calculate the minimum time interval to observe these two peaks independently. And you will see the complex, and your mind go to coordination compound, and you will search the solution in the coordination compound, and it will appear that it is a very tough problem from coordination compound, but it is a very easy problem from the physical spectrum. Now we have to determine the minimum time interval to observe these two bands separately. Delta T is equal to 2.65 into 10 power minus 12 centimeter inverse second divided by delta nu bar, or delta T is equal to 2.65 into 10 power minus 12 centimeter inverse second divided by 2050 minus 2030 centimeter inverse. That is the bandwidth. Bandwidth ये है. और delta T is equal to 2.65 into 10 power minus 12 divided 2 into 10 power 2 second or that is delta T is equal to 1.325 into 10 power minus 14 second. That is the answer. No, we cannot observe these two bands independently because our any instrument, our any spectrometer, XYZ, any instrument related to any spectroscopy, vibrational, rotational, that is work, maximum relaxation time, maximum हम लोअर जो जा सकते हैं 10 पावर माइनस 12 सेकेंड तक. Only we go up to picosecond. Less than this, we cannot observe the band separately, and it is true in the titanium. Remember the coordination compound. That is, in titanium we get a broad band. We get a broad band, very broad band, starting from 20,300 centimeter inverse and at 20,500 centimeter inverse. But these two bands never separate. That is, in a phenomenon called as dynamic John Taylor. Dynamic John Taylor effect होता है. So that is the matter of coordination compound. Our matter is only that why these two bands cannot be separated. So two bands cannot be separated because relaxation time is very low, much below 10 power minus 12 seconds. Now, it is slightly lengthy problem. We have to determine the bandwidth. We have to determine the bandwidth. Now, two electromagnetic radiation two electromagnetic radiation having frequency 500 megahertz and 535 megahertz. Determine the minimum time to separate these two bands. To separate these two bands. Now it is in frequency. It is in frequency. So either we have to change it into wave number. Either we have to change into wave number, which required a formula of delta nu is equal to 35 megahertz or that is delta nu bar C is equal to nu lambda, or that is nu upon nu bar, because nu bar is equal to 1 by lambda, or nu bar delta nu bar is equal to delta nu upon C, or that is delta nu bar is equal to delta nu 35 into 10 power 6 second inverse, or that is C 3 into 10 power 10 centimeter per second, cancelled out, or that is equal to 35 by 3. 11.66 into 10 power 4 centimeter inverse. Very broad band. Now relaxation time delta T is equal to, that is 2.65 into 10 power minus 12 divided by 11.66 into 10 power, that is nearly 10 power minus 15. Nearly 10 power minus 15. Or you can do second method. You can change the formula. Delta E into delta T is greater than equal to H upon 4 pi. Delta E is equal to H delta nu into delta T is greater than equal to H upon 4 pi, or that is cancelled out. Delta U delta T is greater than is equal to 1 upon 4 pi. Now you can determine directly. So one thing is very clear, that as relaxation time increases, band broadening decreases. But one thing is also very clear, that band broadening is a fact. Only atomic spectra in the gas phase, are line spectra. When you draw the Bohr's model, that is Lyman series, Paschen series, you draw the line. That is only a spectra which can be in the sharp band spectra, as sharp as that it is converted into line spectra, thin line spectra. Now, after the broadening of spectra, after the band broadening, now our spectra look like this. That is like this. Y-axis is always fixed. y-axis always represent intensity. Y-axis हमेशा intensity. Always. We have freedom on x-axis. That is nu bar, lambda, or frequency as our requirement. Whenever we study the UV spectra, we take lambda. Whenever IR, we take the a study of wave number. In rotational spectra, wave number. In case of Mossbar spectra, we take frequency directly. So as per requirement, we can change the parameter of x-axis, but y-axis is always intensity. Now spectra is like this. It is intense spectra. It is intense spectra. It is less intense, moderate intensity, moderate intensity. So there are three types of intensity. Intense spectra, high intensity, moderate intensity, very low intensity. What is the reason for this? Now today, last topic is intensity. A very broad discussion. Intensity. On what factor intensity depends? How we get broad spectra, moderate spectra? Yeah. Intense spectra, moderate intense, high intensity. So, first factor, intensity depend upon selection rule. Selection rule. Selection rule. Selection rule are quantum mechanical rule. Selection rule is quantum mechanical rule. Selection rule are quantum mechanical rule to control the transition. To control the transition. It is specific to each spectra. Each spectra. That we will discuss in individual spectroscopy. Whenever we start individual spectroscopy, first thing to study that what is selection rule for this spectroscopy. But whatever the selection rule, one thing is very clear that all selection rule allowed spectra are all selection rule allowed spectra are intense. Are intense. All selection rule allowed spectra are intense. बिल्कुल होना ही होना. All selection rule allowed spectra are intense. Like for example, यहाँ पे हम example, only I am taking example, we will study separately also. That is, during electronic transition, selection rule is, that is, delta L must be plus minus 1. Elaborate. Laporate rule. It is selection rule that delta L must be changed plus minus 1. Now, see the s orbital to p orbital to d orbital to f orbital. S orbital, p orbital, d orbital, f orbital. ये देखिए, ये देखिए, that is selection rule square. Selection rule square for electronic transition. Now, S2P delta L plus 1. Now, P2D plus 1. D2X plus 1. F2D minus 1, minus 1, minus 1. So, S2P transition is allowed. P2D transition is allowed. Delta L means, are you understanding? L. What is L? What is L? L यहाँ पे क्या है?
Azimuthal quantum number.
Azimuthal quantum number. Azimuthal quantum number for s orbital 0, p orbital 1, d orbital 2, f orbital 3. So change in. So these are allowed transition. S to F, forbidden, 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 forbidden. D transition is forbidden. That is, ये देखिए, S2D delta plus 2 not allowed, not allowed. So what is the conclusion? Horizontal allowed, vertical not allowed. Horizontal, all horizontal transition are allowed. S to P to D to F allowed. Vertical not allowed. S to S, P to P, D to D, F to F not allowed. And also jumping is not allowed. Jumping is not allowed. S to D not allowed. P to F not allowed. F to P not allowed. D to S not allowed. So that is only example of the selection rule square for electronic transition. FF transition is forbidden, DD transition is forbidden, S2P transition is allowed. Now, which of the following transition is allowed transition? Which of the following transition is allowed? Which of the following transition is allowed? B is allowed. Why not? Why not D? Why not D? D is also S2P transition.
So degeneracy is different.
Spin multiplicity
This
should not be
electron, इस इलेक्ट्रॉन का ट्रांजिशन हो रहा है.
Yes.
Not allowed, because during electronic transition, delta S also must be zero. Spin state of electron does not change. Spin state of electron does not change. Here, minus half. Here it become plus half. Downward spin electron become upward spin. So it is not allowed. So both the rule must be followed. Delta L must be plus minus 1. Delta S must be 0. Both rule must be allowed. Must be followed. Now, in the atomic spectra of calcium, in the atomic spectra of the calcium, brick red color is observed. In the atomic spectra of calcium, brick red color is observed. It is due to which transition? It is due to which transition? It arises due to which transition? That is that is 3s22 4d0 3s22 3p0 sorry 4p0 3s2 2 4f0 2p6 2 4d0. It arises due to which transition? Here also we have to use the concept of that is this S2P transition. S2P transition. Which of the following correctly represent the allowed transition of electron from n is equal to 2 to n is equal to 2? That is A 1s1 2 1s B 1s1 2 sorry 2p C 1s1 2 2p D 1s1 to 2s. Which is the correct representation?
C.
That is C. Delta M, delta S. Here 0 plus 1. Here plus 1 plus 1. Here plus 1, 0. Here 0 plus 0. Our selection rule is plus 1, 0, which is matches with this. That is C. So these are problem related directly to the selection rule. Directly to the selection rule. Now, but all selection rule allowed spectra having not same intensity. Not having same intensity. Intensity of selection rule allowed spectra. Intensity of SR allowed spectra. Selection rule allowed spectra. Intensity of selection rule allowed spectra. All selection rule allowed spectra are not equally intense. What is the reason for this? Intensity of selection rule allowed spectra depend upon transition probability. Transition probability. Transition probability. Transition probability depend upon relative population of population, the difference between ground state and excited state. And excited state. Higher the population difference, more will be transition probability. Because transition only take place. Because transition only take place till the population of ground and excited state become equal. Because transition only take place till the population of ground and excited state become equal. Consider a case. Consider a case that is ground state, excited state. 3 molecules, 1 molecule in excited state. How many molecule can undergo transition? How many molecule can undergo transition? Only one. Only one. Only one molecule can undergo transition. Because if one molecule undergo transition, population of ground and excited state become equal and transition will stop. So how many pulse of radiation is observed? Only one pulse. One pulse is observed. One pulse is absorbed. Its spectra will be like this. Suppose its spectra is this. One pulse spectra is this. Now, seven, one, GS, yes. How many molecule can undergo transition? One molecule. Now it becomes 6 and 2. Two molecules. Now it becomes 5 and 3. Third molecule. Now it becomes 4 and 4. How many transitions take place in the second molecule? 3 transitions. It absorbs the 3 pulse of the radiation. 3 times it absorbs radiation. 1 pulse, 2 pulse, 3 pulse. It absorbs. And now its spectra will be 3 times as intense as this. 3 times. 1 pulse, 2 pulse, 3 pulse. 3 times more intense. So as a general rule, higher the population difference between ground and excited state, more will be intensity of spectra. More will be intensity of spectra. Now, population of any state, that is Boltzmann formula. Boltzmann partition. Boltzmann partition. Lower state, upper state. Delta E. According to Boltzmann partition, NU upon NL, population of lower state, population of upper state ratio is equal to GI exponent minus delta I E upon KT. That is the formula for distribution of population. NL, population of lower state. lower state, NU, population of higher state, delta E, energy gap, T is temperature, in Kelvin, K is Boltzmann constant. इसको जनरली हम KB लिखते हैं. KB is Boltzmann constant. 1.38 into 10 power minus 23 joule per Kelvin. GI is degeneracy. GI is degeneracy. GI, degeneracy. Degeneracy. For all spectroscopy, it is equal to 1, except for the rotational spectra. Rotational spectra में इसकी value 1 नहीं होता. But in all other spectra, it is equal to 1. That is the formula for population determination, and it is very clear that higher the energy gap, more will be population difference. Higher the energy gap, more will be population difference. Lower the temperature, more will be population difference. Population difference is proportional to energy gap. Suppressing, yes. Suppressing, asked your question.
No, sir.
You raised the hand.
Sorry, sir.
No question. Population difference is directly proportional to energy gap. And population difference is inversely proportional to temperature. Temperature से inversely proportional है. Intensity directly proportional to energy gap, inversely proportional to temperature, because population difference, higher the population difference, more will be intensity. Delta E, electronic, is greater than delta E, vibrational, is greater than delta E, rotational, is greater than delta E, ESR, is greater than delta E, NMR. Inherently, electronic spectra are more intense as compared to vibrational spectra, as compared to rotational spectra, as compared to ESR. as compared to NMR. NMR is the least intense spectra. To increase the intensity, NMR is always done at low temperature. NMR done at very low temperature. पता है ना? 1.82 Kelvin liquid helium temperature. NMR magnet is placed in helium, liquid helium. So that because population difference is very small. निकाला?
यस सर।
हाँ बताओ।
सर ये 1.8 केल्विन मींस ये नहीं समझ में आ रहा है, मतलब उस टेम्परेचर में रखना पड़ता है
मैग्नेट को एनएमआर में।
सर इसके अकॉर्डिंग तब तो एनएमआर कूलेस्ट टेम्परेचर में उसे डेटा मेजर किया जाना चाहिए। तो
एनएमआर यस यस,
बट सर वो तो नॉर्मल ही मशीन होता है, ऐसा कुछ टेम्परेचर लो दिखा नहीं मैंने कभी।
टेम्परेचर लो
नहीं आई थिंक वो जो नॉर्मल मशीन ही दिखा है, वो जैसे मैंने एनएमआर को देखा था मशीन को।
हाँ।
उसमें ऐसा कुछ तो दिखा नहीं कि लो टेम्परेचर करने के लिए कोई पर्टिकुलर सिस्टम है उसपे
ना। पर्टिकुलर सिस्टम थोड़ा ही होता है, उसके इंस्ट्रूमेंटेशन में जाओ ना। तो क्या होता है, ये मैग्नेट होता है दो बड़े बड़े।
यस सर।
इस मैग्नेट में जो चैम्बर होता है ना, उसमें हम लिक्विड हीलियम फिल करते हैं।
ओके।
लिक्विड हीलियम एडियाबेटिक डीमैग्नेटाइजेशन करते हैं, जिससे कि टेम्परेचर जो है वो कूल हो जाता है।
ओके सर।
तो जैसे ही हम इसमें प्रोब डालेंगे, प्रोब it will create the population difference, and thereafter, because in NMR energy gap is so small that we have a population difference of 1 molecule in 2 million. In 2 million, we have a population difference of only 1 molecule. That is the case of NMR.
Okay.
That's why NMR instrument is costly.
Okay.
Electronic spectra instrument, you can buy in 25 lakh. 25 lakh. And minimum 2 crore. Minimum 2 crore. Basic model, 60 megahertz. 2 crore. Due to instrumentation. That is the fact. Now, so inherently, electronic spectra is intense spectra. Vibrational, less intense, but intensity is good. Rotational, less intense than vibrational, but intensity is good. ESR, and all these spectra, instrumentation is at 25 degrees centigrade. Only in the Raman mode, in the vibrational spectra, we go to high temperature. High temperature पे हम जाते हैं. Otherwise, all these spectra, instrument can operate, instrumentation can be done at room temperature, 25, except NMR. Now, problem related to population. Problem related to population. A vibrational state having energy of 1.38 into 10 power minus 21 joule. A vibrational state has an energy gap of 1.38 into 10 power minus 21 joule. Has a ground state population of has a ground state population of 1000 molecule, determine the upper state population at 27 degrees centigrade. Assuming degeneracy is 1. Assuming degeneracy is 1. Now, very clear formula, Nu by Nl is equal to exponent minus delta E upon Kt, or that is exponent 1 minus 1.38 into 10 power minus 21 divided by 1.38 into 10 power minus 23 into 300 Kelvin, joule per Kelvin, joule, that is exponent minus 1 by 3, or that is upper level population is equal to 1000 divided by e power 1 by 3. That is equal to what is answer? What is population? 720. 720. Now in this time, in this examination, I think in CSIR net calculator was allowed. I am wrong or right?
Yes, sir. Allowed, sir.
Allowed था ना? So calculator is allowed. Otherwise, your option in CSIR net will be in this form. 1000 upon e power 1 by 3, 1000 upon e power minus 1 by 3, 1000 upon e square, and like this, without calculation. But
Sir,
now calculator is allowed.
सर
Therefore,
वैल्यू 1.22 के आसपास है
1 point
122.62
122.62 आ रहा है ना?
यस
हमको भी ऐसा लग रहा था. हम भी कैलकुलेटर से एक बार देख लेते हैं. नहीं 720 आ रहा है. इट इज 720.
Okay, sir. I can check.
I think it is e power 1 by 3 is e power 1 by 3 is 1000 divided by 1.389, that is 1.7, yeah, 719.7. Now, in a system of 11-fold degeneracy, in a system of 11-fold degeneracy, 11-fold degeneracy in ground state and 6-fold degeneracy in excited state, determine the energy gap at room temperature. Determine the energy gap at room temperature if population of both state is equal. If population of both state is equal. ये देखिए, in this problem only modification is Nu by Nl is equal to Gu by Gl degeneracy exponent minus delta E upon Kt. According to our problem, Nu by Nl is 1 because both states have same population. It is 1. Gu is equal to 6. Gl is equal to 11. Exponent minus delta E upon Kt. That is exponent delta E upon Kt is equal to 11 by 6. Is it clear? Is it clear?
Yes, sir.
11 by 6 because negative sign we change it into positive. Now, delta E is equal to Kt ln 11 upon 6, or that is delta E is equal to 1.38 into 10 power minus 23 into 298 into log of approximately 2. But since calculator is allowed, point 6061 point ln 11 by 6, that is point 6061 और that is equal to ये आ जाएगा। क्या हो रहा है? 249, that is 2.49 into 10 power minus 21 joule. In this energy gap, very interesting problem. That is next one, very interesting. That is calculate the temperature. Calculate the temperature at which upper state is 20% as populated as calculate the temperature at which upper state is 20% as populated as lower state at a energy gap of at a energy gap of at a energy gap of 1.6 into 10 power minus 19 joule, assuming degeneracy of both state as 1, now Nu upon Nl, the degeneracy of both state is 1, so exponent minus delta E upon Kt. But according to problem, it is 0.2 Nu upon Nl is equal to exponent minus 1.6 into 10 power minus 19 divided by 1.38 into 10 power minus 23 T, or that is exponent minus 1.6 into 10 power minus 19 upon 1.38 into 10 power minus 23 T is equal to 0.2, or that is आ जाएगा। that is T is equal to 1.69 into 10 power minus 19, 1.38 into 10 power minus 23 into 1.609, or that is equal to 1.609, 1.609 cancelled out, or that is 10,000 divided by 72 7249 Kelvin. That is the case of electronic energy. That's why AAS, atomic absorption spectra, required a very high energy source, because only for 2% population, only for 20% population, we had to heat at 7249. For a spectra, at least we required 2% population. So we use the plasma source to achieve the high temperature. ICP. This source are utilized.
सर वैल्यू एक्चुअल में आ रहा है 7246.37
7 to
72 7246.37
46. 46.37. No.
37 no sir okay 37.
So that is the temperature. Such a high temperature is required for excitation of atom. So intensity of a spectra depend upon population difference. And if population difference is less, we have a option to go for lower temperature. लो टेम्परेचर पे भी हम जा सकते हैं अगर पॉपुलेशन डिफरेंस कम है. नाउ these are the introduction of spectroscopy, and our first chapter is completed. Now individual spectra, we will start with rotational spectra. In this section of individual spectra, we will start with rotational spectra. Then we move towards the vibrational spectra, both harmonic and harmonic. Then coupling of rotation and vibration, rotational vibrational spectra. Then we stop at this point and go to Raman spectra, that is a scattering spectra. Thereafter we go to electronic spectra, NMR and ESR. A complete physical and mathematical analysis of these spectroscopy, including the source. What is the source utilized in these spectra? Like here in AAS, I suggested plasma source or ICP. So in every spectra, we have a particular source to generate the wavelength. So that will be rotational spectra will be started from next class. And that is one of the interesting and important spectra.